Hi everyone, I'm Verona, and today I'll be sharing a bit about our work titled Leave a Trace, Recursive Reasoning about Deceptive Behavior, which was done in collaboration with Sarah Wu, Eric Brockbank, and Tobias Christenberg. In this work, we explore how people plan misleading actions, and how observers reason about evidence left behind by such deceptive actors. So to study this, we designed a grid world-like environment with two agents in an apartment. One of two agents walks to the kitchen to grab a snack from the fridge, and on the way back to the room, they leave behind some crumbs, which acts as physical evidence for an observer. We ran two experiments. In the first experiment, participants played the role of a suspect, so they had to draw a path from the fridge and back, and we had two conditions. In the first condition, called the naive condition, participants were simply told to get a snack, but in the sophisticated condition, they were told to steal a snack and avoid getting caught, knowing that they would leave evidence behind. In the second experiment, participants became detectives. So similar to the first experiment, we had two conditions, naive and sophisticated condition, and in each trial, participants saw the final scene after someone had stolen or taken a snack and left some crumbs behind, and they were asked to judge which agent was the most likely thief. To model people's planning and reasoning, we developed a computational model called the RSM, or Recursive Simulation Model. The model has three main components: a path planning mechanism for suspects, an evidence generation process, and an inference mechanism for detectives. It defines different levels of reasoners for suspects and detectives, and it assumes that they recursively reason about one another when planning or making inferences. So to start, we have a naive suspect who only cares about getting the snack efficiently, and so they plan pretty short and direct paths. Next, we have a naive detective who assumes that the suspect was naive and simulates suspects taking efficient paths. Then we have a sophisticated suspect who reasons about how their paths might be interpreted by a naive detective, and so they plan more strategically, and they might take paths that might mislead a naive detective to think that it was the other agent who stole the snack. And finally, we have a sophisticated detective who understands this potential for deception, and so when they simulate the suspects, they simulate them as being deceptive, and takes this into account when evaluating the evidence. So in addition to the recursive simulation model, we tested a few other models. We had two variants of the RSM. The first is one in which the paths are sampled uniformly, and so this model does not distinguish between the naive and sophisticated agents. The second variant is one in which we use the paths that were generated by participants in our experiment. And then we also had a heuristic model, which assumes that people don't simulate paths, but rather they use visual-based heuristics when making inferences about the culprit. And finally, we had GPT-4o generate paths and make predictions to test whether current multimodal models can do the kind of physical and causal reasoning required in the task. So what kinds of paths did suspects take? So in experiment 1, we found that participants were pretty skilled at planning deceptive paths. And so when they were just naive suspects, which we can see on the very left-hand side here, they took very efficient direct paths. But when they were sophisticated suspects trying to steal a snack, they took significantly longer and more roundabout paths on the way back from the fridge. So in this top left figure here, we can see the kinds of paths that were generated by the participants, the RSM, GPT-4o, and the uniform model on a select trial. And so in general, the paths that were generated by the RSM seem to closely match those of our participants, unlike the other models that we tested, like GPT-4o and the uniform simulation model. For GPT-4o, it only tended to generate very short direct paths, even in the sophisticated condition. And for the uniform simulation model, it always generated very long paths. We also computed the Earth mover's distance between the path distributions generated by participants and the models, where lower values are better here, and similarly found that the RSM performed the best. Now, what happens when people become the detectives? So when participants had to infer who the thief was, they became much more uncertain about who the suspect was, especially when they thought that the suspect could be sophisticated and deceptive, compared to when they judged a naive suspect. So it seems that while people are able to plan easily, deceptively, reasoning about a deceptive actor seems to be much more cognitively challenging. And so when we compared the models, the RSM explained human judgments well, and similar to the suspect experiment, GPT-4o struggled to capture people's inferences, further highlighting the kind of complexity that this kind of social reasoning requires. However, we also found that simpler Non-simulation based models, like the heuristic model on the far right here, also perform very well in both conditions. And so this kind of suggests that when we face a complex social inference, people might be falling back onto simpler reasoning strategies. So in conclusion, our findings suggest two main things. People are pretty adept at acting as deceptive suspects, showing a sophisticated ability to plan actions with an observer in mind. However, as detectives, people found it difficult to reason about these deceptive plans, leading to greater uncertainty. And so this points to possible limits in our ability to perform multi-level recursive mental simulations. For future work, we hope to find ways to better tease apart the different kinds of strategies that people are employing, and we plan to extend this paradigm by adding more types of evidence, such as sound, to explore how social reasoning adapts to even richer environments. Thank you.